Welcome back. In this video, we're going to look at the first law of thermodynamics, and we're going to build on what we just learned about the two mechanisms for energy transfer. That is to say, thermodynamic work, which involves macroscopic displacements of coordinates associated with the system, and heat. Now, the first law of thermodynamics is really just restating the conservation of energy theorem, but now in the context of the two mechanisms for energy transfer. So we write now that the differential change in the internal energy of the system, which we write with the symbol U for the internal energy, is equal to the differential flow of energy in the form of heat and the differential flow of energy in the form of work. Okay? And now I can expand out the expression for work that I gave in the earlier slides, and you can see now I have full expression here where I include all the macroscopic displacements. And so for a given system, there'll be beta possible macroscopic displacements that will lead to work being done on or by the system. Okay. Now, it's important to keep in mind that the internal energy is a state function. So it's independent of the path. So it only depends upon the initial and final states. It doesn't matter how you connected those two states. That difference in energy is always the same no matter what path you chose to go from A to B. So this delta U is always identical, but evaluating it in terms of the heat flow and the work, the energy that flows at work, is all path integrals. So the integral for the heat and the integral for all these different types of works are going to be path integrals, and so we'll learn later how we're going to tackle these to get the actual change in the internal energy. Also, keep in mind that we have sign conventions in thermodynamics that whenever the system gains energy, delta U should be positive. Whenever the system loses energy, delta U will be negative, which should be intuitive. Also, the same is true for work and heat. So if work flows in, if there's energy flowing into the system as work, then that work is positive. If energy is flowing out of the system as work, then that work is negative. Similarly with heat, if heat energy is flowing into the system as heat, then the heat is positive. If energy is flowing out of the system as heat, then the heat is negative. Now be careful, there are some engineering books, well, most engineering books, and older physics books where they reverse the sign of work. So if you see the first law is written as du is equal to dq minus dw, you're looking at an older physics book or an engineering book. And that's just done because the perspective of, that work is something that you extract out of the system. So in that mindset, it was a positive quantity. But it's not really consistent with, with the way we define energy here. With the sense of the energy of the system going up or down. So just keep that in mind. You won't have to worry about it in this class, but I'm just saying that if you look at other textbooks, you might find that confusion there. Okay. Now, if we decided that we wanted to prevent all work from happening, if I made all of these macroscopic displacements go to zero by somehow preventing the system from having a volume change, from preventing any kind of magnetization of the system or any kind of expansion of the surface area, or all those possible works that we saw in this table here. If we could prevent all of these displacements, then what would happen is that this term would go to zero and we'd have only the heat as the source of energy transfer between the system and the surroundings. So the change in the internal energy would have to be entirely due to heat flow, and then we can try to measure the change in the energy by measuring the change in the temperature of the system, and the proportionality constant for that is the heat capacity. Heat capacity relates the change in the energy to the change in the temperature. If you remember in the chapter on the kinetic theory of gases, we saw that the energy is linearly proportional to the temperature of the system, okay? Now, in this case, I'm using a subscript here with curly brackets, and I'm writing ZR to represent the fact that all of these displacements are held fixed. They're all constant for the process, so that we're clear how this was happening. So when I write C as the heat capacity, I'm writing C with a subscript curly bracket ZR here to indicate that that's the heat capacity when all of those macroscopic displacements are held fixed, okay? And that And that C actually is then very simply related to the energy. It's just this is kind of obvious, restating the obvious, the partial derivative of the internal energy with respect to temperature with all of those displacements held constant is what's called the heat capacity in that case. Now, this is a little confusing sometimes, but all thermodynamics textbooks will refer to this quantity as CV. So it's telling you this is the heat capacity with the volume held constant. But it's actually more than the volume. It's all the macroscopic displacement. All of these are held constant. But the symbol V is just used here to represent the fact that the volume is held constant, because that's generally what all people are thinking about when they think about work, is just PDV work. But in this case here, when you see CV, it really implies that no work is allowed. Okay, I'm sorry for the confusion, but that's not my fault. Okay. Now, preventing all work from happening and only allowing heat to transfer, is definitely one way in which you can get at the change in the internal energy for any process. But there are a lot of processes where you don't want to have all the work suppressed. You want to have some work flowing at the same time. Energy flowing is work, and so it's not a very practical solution to just say that this is how we're going to measure the energy by preventing all work from happening. And in fact, actually, if you go into the lab and you're trying to measure the change in energy for a chemical reaction, and you want to do it this way by preventing all work, then you'd have to build a reaction vessel where the boundaries, the walls of this reaction vessel are rigid, so that there can be no volume expansion. So generally this is made out of some kind of really heavy stainless steel. It's called a bomb reaction vessel. Probably use the word bomb for the reason that if you have too much energy in that reaction and the pressure increases to the point that the walls can't sustain that constant volume, then it explodes. And you might have damage to the lab or injuries to the people working around it. So it's not an easy experiment to do these kind of no work experiments, what we call constant volume experiments. So for that reason, we want to look for other ways in which we can study the thermodynamics of the system and not have to look at just thermodynamics under no work conditions or constant volume conditions. But there are ways in which we can get at other types of state functions, energy state functions, that will be proved practical. And probably the one that you're most familiar with is the enthalpy. So this is an energy state function that's very useful for isobaric thermodynamic processes. So when you go into the lab and you're measuring a reaction in an open vessel, what you do know is that the atmospheric pressure is going to be constant while that reaction takes place. Generally there's some minor fluctuations in the weather that day, but you can approximate it as saying constant 1 atmosphere pressure while that reaction took place. So if you can make that assumption that you're working under a constant pressure, then this definition of enthalpy turns out to be quite convenient. So what we're going to define is a new energy function, H, as defined as the internal energy plus P times V. Now, since U is a state function, P is a state function, and V is a state function, then that means that H is going to have to be a state function also. So for any isobaric process, there will be a differential change in the enthalpy, and that differential change, I'll write as dH. I'm going to put a little subscript here to say that we're going to do this at constant pressure. So I'll put a P down here to indicate that constant pressure. And that's going to be equal to du plus PdV plus VdP. But since P is held constant, this term is going to go away. And so we only have these two terms here for relating the change in the enthalpy during an isobaric process. All right. Now, if I go back to the first law, which tells me what du is just dq plus dw, I can plug that in to this expression here. And then if I expand out all of the thermodynamic work, and I'm going to pull out of my sum the PDV work here. So that's here. So this is going to beta minus 1, where I've pulled out of the beta terms the PDV work. And remember that here we still have this plus PDV, which is over here, which in fact actually will cancel this term. These two terms will cancel each other, and we'll be left with an enthalpy expression where the enthalpy is equal to just the differential flow of heat plus all this work that could happen, except it excludes the PDV work. So if PDV work is the only work that can possibly happen, so you've already eliminated go back to my slide here, already eliminated all these other possible displacements, and PDV is the only thing that you allow, then under a constant pressure condition, then if you get rid of all the other displacements, then dH is equal to just dQ. All right, so for an isobaric process. So generally speaking, when you see this in textbooks, they'll say that dH under constant pressure is just equal to dQ. They won't show you this, but I'm showing it to you to show you that all the work besides PDV work is also present there too, but we generally assume that that's going to be, all these displacements are held fixed, and that's 0 too. Okay, so we can then write down that an expression that's very similar to what we saw before when we prevented all work, but now if we allow PDV work and we allow it to happen under a constant pressure process, under an isobaric process, then dH is equal to dQ, and that's going to be related to the change in temperature through a heat capacity, a proportionality constant, and that heat capacity, which is now going to be written as C sub P, is the change in the enthalpy with respect to temperature at constant pressure. And this process then is going to be a path integral. So if I integrate this, you can see that the heat capacity is dependent on temperature, so that's going to depend on the path here. But delta H is a state function that will be a measure of the change in the energy under a constant pressure process. Okay. Now, again, this was done because this is probably the most classic sort of Legendre transform, which we'll talk about later, that for changing the energy. But this enthalpy function, you can define other types of enthalpy functions where you define other displacements in addition to pressure being held constant. So you might see in a more advanced textbook, something like HZ1, where Z1 is some other work displacement function that's been held constant during the process. But I'm getting into the details here, so I don't want you to worry too much about that. We can just think about enthalpy as following a process that occurs under constant pressure conditions. So one thing we should examine is what is the difference between the constant volume heat capacity, that is to say the heat capacity when no work is allowed, and the constant pressure heat capacity when we allow PDV work, so we allow expansion work. So at constant volume, we know that all the heat that goes into the system will lead to a temperature increase, because all that heat going into the system increases the internal energy, and that's going to be reflected in an increase in the temperature. At constant pressure, some of the heat that goes into the system is going to go into expansion work, so it's going to produce work, which means that there'll be less heat going into raising the temperature. So if you wanted to get the same temperature change as you would get with a constant volume case, you'd have to put more heat in at a constant pressure to get the same temperature increase, because you're losing energy due to the work that's being produced. So we expect that in general that the heat capacity at constant pressure is going to be greater than the heat capacity at constant volume, or when there's no work allowed. Now, for liquids and solids, there isn't a big difference between the two, but the CP is definitely bigger than CV. But in a gas, it's a pretty significant difference between CP and CV. So CP is significantly greater than CV. And I'm going to leave it for you as an exercise to show in the class that CP is equal to CV plus this additional term here, which will increase is what leads to the increase of CP over CV. Now, in a gas, this second term here can be pretty significant. And so what you see is actually in an ideal gas, remember in an ideal gas, the internal energy in the kinetic theory of gases, we saw that the internal energy was just 3/2 RT, right? And you can see that there's no dependence on volume, so du dV is equal to 0. So for an ideal gas, this term is equal to 0, and then you can show that what's left over here will give you basically R, so you can see that CP minus CV is just equal to R. And you can show that also, after you show this, you can show that CP minus CV is equal to R. But in solids and liquids, what we find is that there isn't a big change in the volume with temperature. So this term here, the dV dt at constant pressure, is not that big for solids and liquids. So that makes this term really small. Multiplying by this term means this whole thing is not a big contribution. So CP is approximately equal to CV in this case. So now we can look at some different thermodynamic processes and consider those processes under constant pressure conditions and evaluate their enthalpy changes. So for example, a common one would be phase transitions, where you have a solid going to a liquid phase, or a solid subliming to the gas phase, or a liquid boiling and turning into the gas phase. So these are called fusion for solid going to liquid, sublimation for a solid going to a gas phase, or vaporization for a liquid going to a gas phase. And in all cases, what we have over here is a more aggregated state of matter, and energy has to be put into that system in a transition to cause the solid to go to a liquid, a less aggregated state. So here we have the less aggregated states, and here we have the more aggregated states. Now, for these processes happening under constant pressure conditions, for example, ice melting or water boiling, then we can use the enthalpy to find the change in an energy function for these transitions. So this is a state function which we can determine under these constant pressure conditions. So again, allowing only expansion work and a heat transfer at constant pressure, the phase transitions for a pure substance can be obtained by just measuring the heat flow during an isobaric process. So we will write delta H for the transition. It could be fusion, sublimation, or vaporization is equal to the heat flow under the isobaric conditions. Now, keep in mind also that during these transitions, the system temperature remains constant during a reversible phase transition. Okay, so we'll actually come back to that later when we're talking about entropy changes. Another example is a chemical reaction where we'll have a change in the energy. We go from products to reactants. Okay, it's a sort of simple example here. I have two reactants, A and B, reacting to form C and D. You know, in a balanced reaction, there might be stoichiometries here, so we have maybe 2 moles of A plus 3 moles of B going to 1 mole of C and 5 moles of D. And for this reaction, we can calculate changes in state functions. So it could be energy, internal energies, enthalpies, could be volumes. And we will write for those state functions that the delta X, where X is some generic state function, is just X for the products minus X for the reactants. So an example under say constant pressure conditions, we would write the enthalpy change for this reaction as the products, so the molar enthalpy for C plus 5 times the molar enthalpy for D minus, and then in parentheses, the 2 times the molar enthalpy for A plus 3 times the molar enthalpy for B, and that would give us the delta H for the reaction, the molar enthalpy change for that reaction in this case. All right. Now, if we were working more generally for a arbitrary reaction, then these coefficients here will give the symbol nu here. And so if nu is positive, then those are the values for products, and if nu is negative, then those would be the values for the reactants. So in this case here, this is a nu value of +1, +5, and here this is a nu value of -2 and -3. And so if you would use that, those coefficients, you can write out this expression here in a more general form like this, where nu would take into account whether it's products or reactants. All right. Now, there is one problem with this equation that I've written here or written here, which is that we can't actually measure absolute values of the molar enthalpies. An absolute energy is tricky because where do you decide what zero is? Do you just assume zero as the rest mass from general relativity? So it's not so simple to use absolute molar enthalpies. But it turns out there's a very simple solution here, and that is to use what are called enthalpies of formation. So I'll give you one clear example here, I think, where it shows you how this can be done and you can eliminate all these molar enthalpies. So for example, in this reaction here for the reduction of iron oxide, you can see I have a balanced reaction at the top, and I can write down the molar enthalpy change for the reaction. So I'm going to write down 2 times the molar enthalpy of iron plus 3 times the molar enthalpy of water minus, and then in parentheses here, brackets, I have the molar enthalpy of the iron oxide plus 3 times the molar enthalpy of hydrogen. So these are all absolute molar enthalpies. But what I can do is I can use the reactions for the formation of species, substances, from their elemental states, and use that to sort of eliminate these absolute molar enthalpies. So let me show you how that's done. So let's take, for example, we have water. Here's a compound, It's not an element, it's a compound that's in our reaction. And we know that we can form water from the elements hydrogen and oxygen. So this reaction here has a delta H, and I can write it out here. It's the molar enthalpy of water minus the molar enthalpy of hydrogen minus 1/2 times the molar enthalpy of oxygen. This is what we call as the enthalpy of formation for water from its elements, okay? So this, similarly here, I can take iron oxide, which can be formed from iron and oxygen, its elemental states, and I can write down its molar enthalpy of formation. Now, taking these two expressions here, and now I have written them in terms of absolute enthalpies, but now I have the molar enthalpies, I can rearrange them, and I can rearrange and solve for this expression here for the absolute molar enthalpy of water in terms of its delta H of formation, and here's the absolute molar enthalpies of hydrogen and oxygen, and then I can solve for the absolute molar enthalpy of iron oxide in terms of its delta H of formation and the absolute molar enthalpies of iron and oxygen. And now if I plug these guys into this expression here, here, and there, and if you do some simplification, you'll find that all of the elemental absolute molar enthalpies are eliminated, and all you're left with is the delta H, which is entirely in terms of the delta H of formations for the water and iron oxide here. So this trick here just simply takes advantage that we have these reference states, which are the formation of our compounds from their elemental states and their stable elemental states, and that allows us to rewrite molar enthalpies for reactions in terms of the enthalpy of formations for the compounds that are involved in the reaction. Okay, this is probably a trick that you remember from freshman chemistry, but I just want to go back through it again here. Okay, so we don't have to use absolute molar enthalpies. We can still get the delta H for reactions in terms of other delta H's, specifically here the delta H of formation. Okay. It's also important to understand that as we've written these, we've been defining these as all happening under a constant pressure. I haven't said what the pressure is, but generally we assume it was 1 atmosphere's pressure. But we're going to define a standard pressure of 1 bar, which is approximately 1 atmosphere, not exactly. And at 1 bar is what we call a standard pressure. And we're going to use a little circle up here to represent the fact that this is a standard pressure here. And when we have a quantity that's been measured at standard pressure of 1 bar, then we'll put that circle. For example, here at delta H of formation measured at 1 bar pressure, we'll have a little circle up here to represent the fact that it's at a standard state here. And usually you'll find tables of these delta H's of formation, and you probably remember those from your back of your freshman chemistry textbook, tables of these, and they'll be given to you at, say, 298 Kelvin. So you find tables of delta H formations, standards, delta H's at 1 bar pressure, and they're given to you at 298. But if you need to do the reaction at a higher temperature, well, you can't use the table at 298, but you can adjust the delta H's up to the higher temperature, so they're still at 1 bar pressure, which is the standard state, but now you're going to run them at a higher temperature. And you could do that by just taking advantage of knowing the heat capacity, the constant pressure heat capacity for each of the compounds that's present in your reaction. So you can change the delta H for a reaction, or delta H for any substance, you can change by just integrating it from one temperature to the next. You take the heat capacity and you integrate it from temperature 1 to temperature 2, and you'll find the adjustment, say to go from 298 to say 350, for example. You just integrate from 298 to 350 the heat capacity, and you'll find the adjustment that you add to your value in the table to get to the enthalpy for that compound. But if you take that same approach for the whole reaction, we can actually take the delta H for the reaction, and we can take the derivative with respect to time. This is a trick here we're going to do, and we can then go back to our previous expression here where we wrote the delta H of the reaction in this more general form. And what I'm going to do is write the derivative of that delta H in terms of the sum of all of the stoichiometric coefficients times the derivative of all the molar enthalpies, partial derivative of all the molar enthalpies with respect to temperature at constant pressure, which we recognize all of these as the heat capacity, the constant pressure heat capacity, and so we can replace that with Cp, and this gives us an expression which tells us how to adjust the heat capacity of the reaction from one temperature to the other. So in other words, we can calculate the heat capacity of a reaction, and then we can take the delta H of our reaction at say 298. We can integrate from 298 to say 350 of this quantity here, which is defined here, and this factor here, integrated from T1 to T2, will give us the change in the delta H for the reaction from our initial temperature T1 to T2. So in other words, if you look up in your table of enthalpies at 1 bar pressure and 298, and you want to adjust the enthalpy for the reaction up to a higher temperature, say 350 degrees, then you need to just know the delta Cp, delta R Cp for the reaction, involving all of the species present in the reaction, and integrating that alone is all you need to adjust the reaction up to a higher temperature enthalpy. All right? Okay, that's it for this video. In the next video, we'll look more about reversible and irreversible expansion of gases.